So in this video, we're going to work on defining the concept of work using a dot product. So in physics, work is simply defined as a force vector acting parallel to, and that's the key, parallel to some distance vector PQ. In other words, we move something using a force through some distance from P to Q. So we have a distance vector from P to Q. We move an object from P to Q through that distance vector. And as long as the force is parallel to the distance vector, then work is simply defined to be the force applied times the distance through which the force was applied. And of course, this definition is assuming constant force. And because we have a vector, all we need to do to find a vector parallel to the distance vector, all we need to do is find the size of that vector and then multiply it by the size of the distance vector, and this will give us force times distance. So where we get a little sticky is if the force that's being applied isn't parallel to the distance vector from P to Q. So here's the distance vector from P to Q. We move an object through that distance vector. Well, if the force is not parallel to the distance vector, what we need to do is decompose the force into a component that is parallel to the distance vector and perpendicular to the distance vector. So the component of the force that's perpendicular to the distance vector doesn't do any work, but the component that is parallel to the distance vector does do work. And what we want to recognize is that the force that is the component of the force that is parallel to the distance vector PQ is actually just, this guy right here is actually just the projection onto PQ of the force vector from our previous videos. So if we can project the force onto PQ, then we have the component of the force that's parallel to the distance vector, and then all we would need to do is take the size of that projected vector and multiply it by the distance. And so work is still right here, force times distance. And what we want to do is identify that if we've represented force and distance using vectors, that really all we need to do to calculate work is take the dot product of the force vector and the distance vector. So what we want to do is justify that. So if we have work being defined as the size of the projection vector, so projection onto PQ of the force vector F multiplied by the size of PQ, all we need to do is remember how the projection vector has been defined. So remember from our previous videos, the projection vector itself is defined to be F dotted with PQ, the vector onto which you are projecting. Let's see if I can write this a little better. F dot PQ, and then you divide by the size of PQ, because we're projecting onto PQ. We divide by the size of PQ squared, and then you multiply by the vector PQ, and this gives you your projection. So you multiply by that vector, and then we would be multiplying here by the size of PQ. But remember, we talked about being able to break the size of PQ squared up into two pieces. So if we put one of the size of PQs under PQ, then this is actually the unit vector in the direction of motion. So if I erase the unit vector in the direction of motion, this scalar is the size of the projection vector. So if we want the size of the projection vector, we just need F dot PQ divided by PQ, and then we're multiplying that by the distance PQ, and then the distance PQ divided by the distance PQ is 1, and so we get 1 times the dot product F dot PQ. So it turns out if we have the vector form of the force and the vector form of distance, then we can just take the dot product of those two vectors, which is incredibly easy to do from a calculational standpoint.